In this video and in this playlist, I'm going to start discussing what is often called the foundations of quantum mechanics. And so uh, this name for it is, I don't know, I kind of don't like it because I think it, doesn't sort of portray what the subject matter really is. So I oftentimes think of it as the interpretations of quantum mechanics. And so what I mean by that, so if you've watched any of my videos on my other quantum mechanics playlist, or if you've ever taken like a quantum mechanics class at school or anything, you've probably taken very much what's often called the shut up and calculate approach, which is just these equations can be used to calculate things that give good predictions in experiments. And so don't worry about what's actually going on. Don't worry about, what the wave function means or, what's actually happening there. What matters is that these equations, the Schrodinger equation and things like that, give good predictions. You can calculate it and you can say, I predict that, this percent of the time we'll get this result and this percent of the time we'll get that result and so on. And so, in a lot of those kinds of classes, you don't talk about, what's actually going on behind the scenes. What is the wave function? What does it mean for the wave function to collapse? Why, what does it mean for the particle to be in multiple places at the same time and things like that? And so, foundations of quantum mechanics is what really kind of gets into that. And so, it has a lot to do with the interpretations of quantum mechanics. But it's a little bit more than that, which is why it's probably not usually called just interpretations of quantum mechanics. But so some of the things that will be discussed in this playlist. So we'll talk about the measurement problem, which is just it gets into things like what is a measurement? What do we mean by a measurement? What distinguishes a measurement from a non-measurement? And, how is it that like a measurement with, some equipment that's, sort of quote unquote classical physics is interacting with a quote unquote quantum system? What is meant by that? And so that, are we supposed to divide the world into these realms of the quantum realm and the classical realm and things like that? Then there is the locality and causality issue, which, gets into the whole thing about like entanglement and the collapse of the wave function sort of, communicating with parts of the wave function, arbitrarily far away and saying, we've collapsed over here, so don't show up over there anymore and things like that. And so that is sort of what the locality and causality issue is. Then there is the ontology issue, which is just sort of, so ontology is kind of a philosopher's term for, what exists. So things that exist. What are we committed to saying exists? And so in quantum mechanics, for instance, the wave function. So we call this a probability wave, but probability isn't like sort of a substance or a thing that exists, or at least not classically thinking. But in quantum mechanics, it seems like we're almost committed to saying that a probability is like a thing that exists, that it's something that we, is exists in the world. It's almost something. I mean, with like this stuff with the measurement problem, it's not really something you can touch, but it's something that is, it's a thing out in the world. It's mind independent that exists, and so the thing about that is like, in what way can we say it exists? What is the wave function? What is it describing? And you can get into other things like fields and potentials, and are those just mathematical kinds of things that are useful tools for making calculations in these sort of shut up and calculate kind of approach to quantum mechanics, or are those actually things out there in the world that exist? Is there some kind of substance that we could say is, like the electromagnetic field of which, photons are just excitations in it and so forth. But then there is the interpretation part of it here. And so it's, how to interpret the wave function. And so, like what it means for the wave function to collapse and stuff like that. And so the Copenhagen interpretation is sort of the canonical interpretation, and it's very conducive to the shut up and calculate, because it essentially says you have a wave function, it's evolving according to the Schrodinger equation, and then it collapses when you make a measurement. What's happening in the collapse? What does it mean for a collapse? Don't worry about that. It's just a collapse, and just shut up and calculate. And so that's kind of what the, in very broad strokes, what the Copenhagen interpretation is, which I will, in later videos, I'll discuss in quite a bit more detail, but that is kind of the main thrust of the Copenhagen interpretation. But there are these other interpretations as well. So probably the three biggest ones here are these ones. So the pilot wave interpretation, which in broad strokes says that the wave is something on which the particle is sort of, riding. So the wave is the pilot sort of pushing the particle around. And so that's how you interpret the wave function. The spontaneous collapse interpretation says that the wave function, that collapsing is something that's sort of inherent in the wave function, and so collapses are sort of happening spontaneously all the time, and so we can actually sort of try to incorporate these collapses that are just sort of postulated in the Copenhagen interpretation, and we can try to incorporate those into the theory. Then the many worlds interpretation is the one that says that collapses sort of cause the world to split into multiple different worlds, and so like I said, we'll get into these in a lot more detail in the coming videos here. So Bell's theorem. Bell's theorem is not really an interpretation of quantum mechanics. It's more a way of testing whether the sort of probability of quantum mechanics is actually, inherent, or if there are what are called hidden variables. So, whether the theory is actually complete or not. And so it sort of tells us that we do need to, if we want to, make an interpretation of quantum mechanics, that we do need to take the wave function seriously as a complete description of the particles. But again, we'll get into that in more detail in the coming videos. And so in this playlist, I'm going to be following this book right here. So this is going to be the guide that I use for the videos in this playlist right here. So it's the Foundations of Quantum Mechanics. So an exploration of the physical meaning of quantum theory by Travis Norson. And so the link to that on Amazon will be here, and so the lecture notes will be linked to in the description down below. So if you want to get this book for yourself, then you can find the links there. So in this first video, I'm just going to sort of introduce us to sort of what is known as the classical view of physics. And so because we'll be sort of using this term a lot throughout these videos when we sort of compare quote-unquote classical physics to the quote-unquote quantum physics. And so in classical physics, we have what is often called the Newtonian view of the world. So this one is the one where the world kind of obeys the three laws of motion. So at every level, big and small, so at the, sort of cosmic scale and at the very small scale, everything is obeying the laws of motion that Newton put forward. And so these are the three laws of motion. And I just copied these from Wikipedia, actually. So the first one is a body remains at rest or in motion at a constant speed, or velocity would probably be a little bit more precise of a term, in a straight line unless acted upon by a force. And so this is just the law of inertia here. So when a body is acted upon by a force, the time rate of change of its momentum equals its force. And so that is, essentially what this is saying right here. So the force is equal to the change in momentum, p, in time. And so we have momentum being equal to m times v, so the mass times the velocity. The force is just equal to the mass times acceleration, and the net force on some object is just equal to sort of all of the forces acting on it. So if we have an object right here, and we have some force pushing this way, one pushing this way, kind of a small one pushing this way, and then a very large one pushing this way, we sort of add up all the net forces, and we'll see that this one right here is sort of winning out, and so you will have an acceleration in this direction right here. So, all of the forces added up, and then you just sort of take what the sort of net direction of the acceleration is for that object. All right, then we have the third one here, which is if two bodies exert forces on each other, these forces have the same magnitude but opposite directions. And this is very related to what the second law is, but it's just if you have a force pushing, say, to the right, then it will have a equal and opposite force pushing to the left. Then we can sort of derive Newton's law of gravitation from this. So the law of gravitation is a force here, and it's dependent on this constant here, this capital G, then the two masses that we're looking at here, and then the distance between them, where this capital G is equal to this right here. It's just a proportionality constant. But if we look at sort of three bodies here, we can look at the forces acting on them here, where this number 2 here, it has a force acting this way caused by this green one here, which has a force acting that way. This one and this one are both acting on each other, as are this one and this one. And then this is sort of a space-time diagram of what's going on over here, where we can think of this red and this orange one here as being like a binary star system that are orbiting each other. Then this green one here is like a planet that is orbiting that binary star system. And so in the Newtonian view of physics, we take this time slice here, and that time slice is just flat across all of space. So time, as we see here, is sort of moving in the upward direction. Then we're just looking at 2 dimensions of space here. And so in Newtonian physics, this time slice, so it doesn't have the sort of relativistic corrections or the relativistic view that we get from Einstein, and so we just have there is a definite sort of slice of space in every time, and so each sort of time would have its own slice of space that's just even across all of space. And so that is sort of the Newtonian view of space. So although Newton didn't know how gravity works, he didn't actually think that it was instantaneous, which would mean that it was non-local, but the idea that gravity works instantaneously is often ascribed to the so-called Newtonian view of physics. And so a lot of times this is kind of the ambiguity of calling things the classical view. So in the classical view, as we talk about it now, we probably wouldn't say that that gravity is instantaneous, because we know about special relativity and stuff like that. But a lot of times the Newtonian view, at least anyway, is sort of said that gravity works instantaneously. But usually when I talk about the classical view of physics, we will at least be incorporating Einstein's special relativity, if not general relativity, into it. All right, so another part of the classical view of physics is Maxwellian electrodynamics. And so this is an important part of our classical view of physics as well. So similar to Newton's gravitation, we have Coulomb's law for electrostatic forces. And so it looks very similar to Newton's law of gravitation, where it's an inverse square law, where we have these two charges here acting on each other, then this proportionality constant, which is equal to this right here. Then we have electric fields, which are just the force that we get here from the Coulomb electrostatics divided by one of the charges here, which gives us just a single charge in that numerator. And so it looks like this. And so an electric field is essentially, what force you would have if you then inserted another charge right there. And so when you're doing, sort of like freshman level physics, a lot of times you think of like a test charge. And so you have like an electric field like this sort of pointing in this direction. And then you take like a test charge, which is just a point charge like that, and say, okay, what sort of effect would that test charge feel? And that's sort of how you test the strength of an electric field. And so the electric field at a point in space, R here, then is this. So we're just adding up all of the sort of contributions of the electric field, and that's called the principle of superposition, where, if we have, the electric field coming from some particle here, but then we also have it from here, and say this one is even stronger, so the electric field is stronger, so we put our test charge here, and we have the weak electric field coming from there and the stronger one going there. They're pointing in opposite directions, so they sort of cancel out proportional to their size, and so we have sort of a net electric field pointing that way. And so that is sort of what that means. Then we have Maxwell's equations here. And so these consist of Gauss's law and Gauss's law for magnetism, Ampere's law, and Faraday's law. And these equations can look a little bit intimidating if you don't really know what they're saying. But what they're saying is actually fairly simple to understand. And so Gauss's law, which is this one right here, just says that the electric field E radiates outward, which is why we take the divergence. So that's what this nabla here with the dot right there says, from a charge density rho. And so where the charge density is just the number of charges in a region. And so we can think about it like this. So we have, some point charges right here in some region. So we can think about the region like this. And so it's just saying that the electric field lines will sort of radiate outward from that region. So they radiate outward from that region. And so whether the charges are positive or negative sort of says the direction of the radiating electric fields. But what's important is just that the electric fields radiate outward. And so what the divergence is saying is just sort of the sort of magnitude of that radiating outward. So, if you have like a single charge there that just has a little bit of charge, then it'll have a smaller divergence than something that looks like this, where we have sort of multiple charges here in this region, and so then the charges are radiating outward from there. Gauss's law essentially says that we don't get that for magnetic fields, and that's why it's equal to 0. So a magnetic field always forms a closed loop. So if we have a magnet here, then the magnetic field lines will look like this and we can sort of think about them continuing through the magnet there. So they will sort of go through the magnet and always form these closed loops, and so they will never have any divergence. So the number of magnetic field lines coming into some region has to be equal to the number of magnetic field lines going out. So a divergence just means, so if we're looking at some region of space here, a divergence just means that if we have sort of field lines coming in like this, then there are sort of more of them coming out than there are going in, or the opposite could be true, because we would have some point charge here that is itself creating more field lines. But with magnetic fields, if we have some region of space, the number of magnetic field lines coming in always has to be equal to the number coming out. And so that's what we mean by the divergence is equal to 0. And in fact, I actually put this here, which is incorrect. This is not the curl of the magnetic field. So it should be the divergence of the magnetic field is equal to 0. So I'll change that in the lecture notes that will be linked to in the description down below. But that should be the divergence of the magnetic field is equal to 0. So then Ampere's law here just says that a magnetic field, which, as I said, always forms a complete loop, which is why we're taking the curl here, is produced by moving electric charges. And so the J is current, so such as moving through a wire. And this right here is the strengthening or weakening of an electric field in space. And so when we have a wire, say, so we have this wire here, and we have electric charges inside that are moving, that is a moving electric field, and so that will actually create a magnetic field. But also, if we have, say, this wire here, and we're sort of increasing or decreasing the number of charges in it, that will also induce a magnetic field. And so that is what these two terms mean. So we have the moving charges here, and then this term right here is just the increasing and decreasing of the strength of the electric field in time. And so that's what this time derivative here is telling us. Then Faraday's law is just saying that a moving magnetic field, so this right here, will induce a closed loop electric field. And so a lot of times in physics, in like elementary physics, what they will talk about. So say you have like a wire here, and you have a magnet here that you are sort of moving back and forth through this wire here, then you will induce an electric field that will cause a current to actually move through here, because you are creating an electric field that sort of moves around in a circle around where the magnet is actually moving. And so that is what the Faraday's law says. So the first two laws here are just sort of telling us about, like, what an electric field and a magnetic field, like how they behave. And then these two are sort of telling us how you induce these fields using sort of the other field. So we can induce a magnetic field using moving charges or changing electric fields, and we can induce an electric field using a moving or changing magnetic field, where a moving and changing magnetic field is sort of the same, because if you think about our example down here, as you move this magnet through this wire here, you are sort of increasing the strength of the magnetic field until you get the magnet sort of right in the center here. Then you are reducing the strength of the magnetic field as you sort of move it out of there. Then there is also, I guess, what we call sort of an honorary Maxwell equation, which is the Lorentz force law that describes how charged particles respond to electric and magnetic fields. And so it's just a force here that has to do with a charge in an electric field and then a charge moving at some velocity through a magnetic field. And so those are sort of the main equations used in electrodynamics. And so electrodynamics is also an important part of the classical view of physics, at least, the Maxwellian electrodynamics, because you can get into quantum electrodynamics, which, brings together electrodynamics with quantum mechanics a little bit. But in the classical view of physics, which is what we've been describing here, we sort of combine the Newtonian view of the world with the Maxwellian electrodynamics, so the classical view, you can sort of either leave in or take out like the Einstein's special relativity. Nowadays, we would probably include Einstein's special relativity as part of the classical view of physics. And so usually in future videos, when I talk about the classical view of physics, we will likely be including Einstein's special relativity in with that. And so, just the idea that uh, there is a sort of maximum speed at which anything can move through the universe, because that's where, the way that quantum mechanics sort of butts up against our intuitions about like locality and causality will kind of come into play. But anyway, like I said, this playlist is going to be looking at what's called the foundations of quantum mechanics. And so we're going to be using this book here to sort of look at some of these different problems up here in quantum mechanics, as well as these interpretations and Bell's theorem, which kind of applies to both of these here. But anyway, I don't want to ramble on too long. I hope you found this video interesting, and I will see you in the next one.